All right. So let's get started today. We're going to be looking at these two limits to start off today, right? Continuing where we left off. How do you find the limit as x approaches infinity of a given function, right? And that's just asking, what is this function pretty much doing as it goes off towards infinity, right? You can also ask it if as it goes off towards negative infinity as well. Now let's see here. Got a couple answers already plugged in. Some people got answers number 1. That's beautiful, and some people are leaving number 2 blank for right now, and that's fine, right? If you're still uncomfortable with how this works out, let's work this through. Okay. So let's take a look here at number 1. The limit as x approaches infinity of 1 over x, right? We need to ask ourselves, what is this function doing as x starts to go off towards infinity, as it goes off towards the right side, right? So as it gets larger and larger, we can say that this thing is approaching, right? We can make a table. That's one way you could always approach these things and try to estimate what is going on as it goes off towards infinity, right? We can say, oh, what's happening at x equals to 1? And then what happens when x equals to 10 and x equals to 100? And then we can go even larger, x equals to 1,000,000, right? And x equals to 1,000,000,000. One more zero. Yeah, one more zero. So we can just plug that in and we can see what is it doing as it goes off towards infinity. So when I have 1 over x here, I have 1 over 1, which is just 1, right? This will be 1 over 10. This will be 1 over 100. This will be 1 over 1,000,000. I'm hoping you can see like what it's trending towards, right? What it's trending towards is 1 over a very large number. And what is that approaching as you make that denominator larger and larger and the numerator stays a 1? When that you'll see that it's approaching 1 over infinity, or in other words, it's approaching 0, right? It's getting closer and closer to 0, but it never quite touches 0, right? But remember, that's the idea of what a limit is. A limit is not what it equals to, it's what it approaches. It's what the y value gets closer and closer to as x gets closer and closer to it, right? Yeah, and that's pretty much it. That's your answer. The limit as x approaches infinity of 1 over x is 0. This function is approaching 0 as it goes off towards infinity because you can clearly see this number is getting larger and larger as x gets closer and closer to infinity. And that would be it, guys. That's all we have to do for this one. All right, now for number 2, when you look at this, oops, over here. When you look at number 2, same concept, right? You can either make a table or you can realize this is pretty much a rational function, and you're basically looking for horizontal asymptotes, right? You're looking for horizontal asymptotes. Now, if you remember back to your pre-calc class or your IM3 class, if you have these things, there's a couple of rules when you're looking for horizontal asymptotes, right, in rational functions. One of them is if you have, let's say, wow, that is not what I want to write with. If you have, I don't know, a times x to the n plus some stuff, right? And then in the bottom you have b times x to the m, right? I have a couple rules here. First rule is if m is greater than n, right, you're going to have a horizontal asymptote every single time at y equals 0. If the denominator's power is greater than the numerator's, right, the degree, I should say, not the power, the degree. If the degree of the denominator is greater than the degree of the numerator, what will essentially happen is, right, if I have, for example, here x to the 3rd over x to the 4th, right, if you simplify it, no matter what, or if you had x to the 50th over x to the 60th, right, what essentially is going to happen is as it goes off towards infinity, the denominator is going to get infinitely larger faster than the numerator. And if that doesn't make sense, just pretty much look at it like this. If you simplify this out, you cancel out the x's, right? Cancel out your variables, and you have the degree that's higher than the denominator. You'll always end up with something where you have a x in the denominator and just a constant in the numerator, right? And as you go off towards infinity, that denominator is going to get larger and larger, and the numerator is just going to stay constant. So if your denominator has a greater degree than your numerator, this will always happen, and you'll always have a horizontal asymptote at y equals 0. That's not the case here, though, right? You guys see that right here? This one has x to the 4th in the numerator and x to the 4th in the denominator. So if you have it where the degree of the denominator is equal to the degree of the numerator, what will essentially happen is you'll be left with just the coefficients, right? You'll be left with just the coefficients. So if I had something along the lines of like 5x to the fourth plus 3x, right, over 2x to the fourth plus 3x squared, right? I know some of you guys are thinking like, well, doesn't this gonna screw this up at some point? No, not really. When we look at rational functions, you mostly just focus on the highest power or the degree, right? And when the degrees are the same, right, I can cancel out all of them with x to the fourth. So what you end up essentially ending up with is something like this. If I divide every single term in the numerator and the denominator by x to the fourth, right, you'll end up with something like this. You don't have to do this, by the way. This is just something just to show you an idea of why this happens. If I divide every single term by x to the fourth, watch what happens. So if I divide this by x to the fourth, come on, knock it, get two together. X to the fourth plus 3x over x to the fourth. So I'm dividing every single term in the numerator by x to the fourth, and I'm going to go down here and do the same thing. Divide every single term in the denominator by x to the fourth. Let me scroll that up. I'll put that back on the screen in a second here. So, and then this will be 3x squared x to the fourth, right? What essentially is going to happen, right? In the numerator, I'm going to have here 5 plus 3 over x to the third. And in the bottom, I'm going to have here 2 plus 3 over x, right? And when you look at a function like this, right, the stuff that's over x, right, if you guys remember from earlier, anything that's over x, it will eventually approach 0 as x goes off towards infinity. So when I look at this function, if I were to take the limit of this and I ask what is happening as x goes towards infinity, right, I'm going to have an infinity over here in the denominator. I'm going to have an infinity over here in the denominator. And those terms essentially will approach 0. Will approach 0. So then you end up with your horizontal asymptote, right, for this case, equaling to 5 over 2. Or in other words, it'll equal to your coefficients divided by each other. It'll be equal to a over b, knowing that your a and your b are your coefficients that are in front of your lead coefficients in front of your, well, degrees, right? Does that make sense? And I think when this is taught to you guys, you're kind of just taught this rule. If the degree is equal in the numerator and it's equal to the degree in the denominator, you just take the coefficients. And now what you're doing in calculus is seeing why that's the case. I'm hoping you're seeing why, right? That is the case. And the reason it's the case is just because of this idea of limits, right? You don't actually get the exact value of what that function is, but you get to see what that y value approaches when you take the limit, right? Anyways, that's a long-winded talk right there just for me to get back to this problem. And pretty much you should have got here. Notice that the degree here is 4 and the degree in the bottom is 4, so they equal each other. So the limit of this thing is going to be equal to 3 over 5, right? I know some of you guys are like, what about that sign, though? So if you break it off and you took a look at that sign, you'd have here sine of x over x to the fourth. And I'm telling you right now, the limit of this, right, if you look at the limit as x approaches infinity of this is going to go towards 0. So that right there kind of just goes off. And again, you're mostly focusing on the highest degree when you're dealing with horizontal asymptotes, right? So those were two basic rules back from pre-calc, remembering the degree of the denominator and the degree of the numerator and comparing the two. So if the degree of the denominator is greater, you get y equals 0. If you have them equal to each other, you have y equals to the constants being divided, right? Bonus one, right? If you have the limit as x goes towards infinity, and you have the numerator greater than the denominator, that limit will shoot off towards either infinity or negative infinity, where we would say then this function doesn't actually approach one number, it goes off forever, and we would just say that that does not exist, right? By the way, some people like to just write down that it goes off towards infinity or it goes off towards negative infinity. These are related to each other. If you tell me that the limit of a function goes off towards infinity, that's just another way of saying that it does not exist, right? It goes off forever. It doesn't actually approach one number. It approaches infinity. All right. Crazy warm-up, but yeah, that's pretty much what we learned last week, right? We did all this stuff with, well, yeah, we did all these problems last week, right? So hopefully this is a nice refresher, because now we're going to go back to our lesson today to finish up, which is vertical asymptotes. Okay, I'm going to give you a second to get your notes ready here for your vertical asymptotes. down, if you might have it from last time, though, vertical asymptotes are simply defined by this limit definition, right? It's basically, you take the limit as x approaches some number, a, some constant, a, from the left side or the right side, and that limit goes either off towards infinity or negative infinity, right? It's pretty much saying that the limit as it approaches from the left side or the right side doesn't exist, right? It either goes off towards infinity or down towards negative infinity, right? Give me 1 second here. Oh, it's still going. Okay, so yeah, hopefully you guys get that down, right? It's the limit as it goes off towards infinity or it goes off towards negative infinity. As it approaches a number, though, not as x goes towards infinity, right? As x approaches a number. So, right, that pretty much defines what the vertical asymptote is. Now, back in your previous classes, you learned vertical asymptotes to occur at specific points, and specifically, I think you only dealt with rational functions, right? I think. And it was always basically, oh, set the denominator equal to 0, right? You guys, does that sound familiar to you guys? Like, set the denominator equal to 0, you got yourself a vertical asymptote there at that point, all right? And that's actually only partially true, right? Only partially true. It needs to not only have the denominator equal to 0, but when you take the limit, you also need to show that it approaches infinity or negative infinity. Okay, let's just do a problem. I'll show you what I mean. So I'll leave that up there. Let's go to this problem right here where it says find the equation for the vertical asymptote for y is equal to 1 over x squared, right? And again, from your previous class, right, you would just say, oh, the vertical asymptote occurs when the denominator is equal to 0. And then we would solve this and say, oh, when does x squared equal to 0? Well, you take the square root of both sides and you get plus or minus x is equal to 0. And plus or minus x is equal to 0 is just equal to 0. So you have here a vertical asymptote at x equals 0, right? Now, that's not essentially like the last bits of it, okay? Next thing you're supposed to do is just check the limit as it approaches 0 from the left-hand side and the limit as it approaches 0 from the right-hand side, right? And you can go ahead and try that and just take a look here. Let's just do it from one side. Let's say I'm taking the limit as x approaches 0 from the positive side of 1 over x squared. What does that equal to? What does that approach? And if you were to plug this into a table, right, what are numbers that gets close to 0, by the way? You guys know? What are some numbers that approach 0? That would be some good numbers to use. You guys should have been doing it for your homework. What are some numbers that are getting close to it? I can't plug in 0, right? 0 is going to give me undefined. 0.1. Very good, Brian. Thank you. 0.1 is a number that gets close to 0, right? And we can try 0.01, right? And we can try 0.001. And then all we got to do is just plug in the calculator and see what is it doing as it gets closer and closer to it. So I'm going to go ahead and do that. I'm going to plug in 1 over, put these in parentheses, 0.1 squared, right? And oh, I get 100. You see that? I get 100 there. So then I try another number. Let's try 0.01. 0.01 and see where that goes. It gets up to 10,000, right? So at here, it's at 100. At here, it goes up to 10,000. I'm hoping that you see the trend of this thing as I get closer and closer to it from the positive side. It's going off towards positive infinity, right? And then we can do the same thing for it as it approaches the negative side, as the limit as x approaches 0 from the negative side, or from the left side, right, of 1 over x squared. And I could do the same thing. I could just try these values out for x that are getting closer and closer to 0 from the negative side, like negative 0.1 or negative 0.01, right? And see what that is. And you plug that in the calculator, and it's going to come out the same thing. This is going to come out to 100. This is going to come out to 10,000. So this is also approaching infinity, right? So what's nice about this is knowing how to find these vertical asymptotes will help you to figure out, can I even take the limit at this point, right? Knowing that there is a vertical asymptote at 0, right? And if I were to graph this, right, I see that as I approach it from the left-hand side, it's doing this thing where it goes off towards infinity. And then as I approach it from the right-hand side, it also does this thing as it goes off towards infinity. And then that means that my vertical asymptote is right here, right at x equals 0. How you guys doing? I know it feels like it's a lot, right? But take it slowly. Like, just understand, like, this is stuff that we've dealt with in the past. A vertical asymptote is nothing new, right? But now we're just now looking at it as the limit, or as we approach it from the left side or the right side. Okay. So let's go on to this one. Find the equation for the vertical asymptote for y is equal to x squared minus 4. I'm not going to ask you to give me this. I'm just going to ask you to try it. See if you can figure out what is the vertical asymptote for this. You don't have to type it in the chat. Just write it out in your notes. We're looking at y is equal to 1 over x squared minus 4. Go ahead and try it. All right. Hopefully you guys remember, right, what we just did there? We were looking for what when you're looking for the vertical asymptotes? You're looking for the denominator to be equal to 0, right? That's one way we could do it when we're looking for these vertical asymptotes. Now, when you solve this, you have two ways. You could add the 4 over and take the square root, or you can factor it and then solve it. But hopefully you guys will see that the vertical asymptotes you get is going to be -2 and +2, right? And the other way we can look at this is graphically, right? Another way we can look at this is graphically. So let me go over here. Let's open up my graph real quick and just plug in 1 over x squared minus 4. And it looks something like this. Right? It looks something like this, where I have, it looks like my two vertical asymptotes was x equals to 2, and I had x equals to -2, right? And let's go ahead and make those dotted, and let's keep them both the same color, so both be blue. So then we can see it right here, right? X equals 2, x equals -2, vertical asymptotes. And if I were to approach those vertical asymptotes from either the left side or the right side, I can see that it's shooting off towards either infinity or it's shooting off towards -infinity. Either way, I would say the limit at -2, as x approaches -2, I would say of this function does not exist, right? I'll repeat myself here. The limit as x approaches -2 of 1 over x squared minus 4 does not exist, right? It does not exist. Now you could say the left side it goes off towards positive infinity, and the positive side it goes off towards -infinity. But remember, infinity and -infinity are still numbers that don't actually exist. They're just this idea that they're going off forever. Okay, so that's that right there. Okay, that's that answer right there. All right, let's take a look at this one. You guys go ahead and try this one, or not try it, but just take a look at this one with me. Find the equation for the vertical asymptote for x squared minus 3x plus 2 over x squared minus 4x, minus 4. Blech, minus 4. So, right off the bat, instinctually, right, from what we just learned, we want to say that the vertical asymptote happens when the denominator is equal to 0, and that happens at x equals to 2, comma, -2, comma 2, right? Now, if we were to say this, though, this isn't true, right? The vertical asymptote does not happen at both these places on this equation. Okay? One thing you need to take into account is simplifying this function, first of all, before you go through with it, right? So we can actually take a look here, and we end up with, in the top, you could factor this, by the way. X squared minus 3x plus 2, that's the same thing as x minus 2 times x minus 1, right? And when I factor that, and I factor the bottom, x squared minus 4, which is the difference of two squares, we get here x minus 2 times x plus 2, right? And the x minus 2's actually cancel out. And when you cancel out the x minus 2, you're actually taking away one of the vertical asymptotes. It's removing one of them. It's removing that vertical asymptote out of the equation. And you can actually check this out. So the function that we end up with, if we simplify this, right, this is actually going to be x minus 1 over x plus 2. And if you test out these two values, if I test out x is equal to negative 2, watch what happens. We have here y is equal to negative 2 minus 1 over negative 2 plus 2, which gives me negative 3 over 0. And that's undefined, right? That's undefined. But if I were to try out x equals 2, right, I get here y is equal to 2 minus 1 over 2 plus 2. And you end up with this guy right here, which is going to be 1 over 4. So at x equals 2, the function is still undefined, by the way. You plug this back into the original function, you're going to get something that's undefined. But if you plug it into the simplified version, you actually get this value. And that's actually a limit value that it approaches. Since it approaches this value and it does not approach infinity, which it does over here, by the way, and I'll show you the graph, that means that the vertical asymptote only happens at x equals negative 2. It does not happen at x equals 2, right? And let's take a look. Watch this. So back over here on this graph, let's go and take a look here. The function was, I don't have to delete all that. Actually, you know what? No, I can't undo. All right, so let's say I have here x squared, right, minus 3x plus 2, right? And I'm going to say that this whole thing is being divided by x squared minus 4. Check this out. It's a new looking graph, isn't it? So this is the vertical asymptotes are still there from last time, right? Just from the last example. But check this out. At negative 2, this function is still going off towards infinity from the left side and still goes off towards negative infinity on the right side. So at x equals negative 2, we still have a vertical asymptote. But look at the part that we removed, the part that we factored and canceled out, right? You see that? It crosses this vertical asymptote. And not only that, as I approach it from the left-hand side, it doesn't go off towards infinity, right? That's the definition of your vertical asymptote. It needs to approach infinity or negative infinity. But it doesn't. It approaches this undefined point right here. And it does so from the right-hand side as well, like so. See that? They're both approaching this point right here. And if we zoom in and we get that closer and closer to that point, it's about 0.24 on the left side, and it's about 0.25 and some change on the right side, which means that if I get closer and closer, this is approaching, right? It gets closer and closer, 2.47, 2.48, 2.49, and this one's going to be 2.53, 2.52, 2.51. It's approaching 2.5. I shouldn't say that. It's 0.25, right? It's approaching 0.25 from both sides. Whereas what we said earlier, for it to be a vertical asymptote, the limit of it as it approaches that random point needs to either be infinity or negative infinity, right? Infinity or negative infinity. And when we look at this graph, it's clearly not infinity or negative infinity. It's clearly a point, right? So the limit there does exist, whereas the limit on this vertical asymptote does not exist, right? So that's that one right there. So I'd say it looks as simple as, oh, just set the denominator equal to 0, but make sure you simplify first and see if there's any removable, right? Removable vertical asymptotes that you have there. All right. So let's go ahead and have you guys try two problems here. I got one right here, and I got two right there. I'm going to go ahead and move your slides onto the next one. And let's go on to here. And you guys can go ahead and start this up. Let's see here. Try these two problems out. I'm going to set a timer for 3 minutes. That's not enough. Let's go 4 minutes. I'll set a timer for 4 minutes for you to try these two problems. And let's see where you guys are at in 4 minutes. Okay? Get out of the way. Oh, no. Stop that. Right. There we go. So I'll set a 4 minute timer. Try these two problems out. See if you can find out what is the vertical asymptote for each of these equations. And I'll open up the pair deck so then you guys can type in your answers for both of them. Yeah, for both of them. Can I do that? Let's see. We'll figure that out. Should be open now. You guys should be able to go to either either page, page 1 and page 2. I have them set up so you can type the answers on separate pages. If it doesn't work or you still need the link, if you need the link again, I'll put it back in the chat right now. You guys are working on that. Wanted to scoot over to the side. I don't know if any of you guys have been appreciating the whiteboard in the background. It changes every day for you guys. Today is potted plant themed. Plotted pants made me laugh, so I had to share this one with you guys. Yeah. Thanks. It's not me who draws it, by the way, but I was hoping that you guys would appreciate it. All right, got about 2 minutes to go. Hopefully you guys are getting the answers for your vertical asymptotes, right? Just to write down the equation for your vertical asymptote, remember it's x equals, right? So you write x equals for your vertical asymptote, and then do it the same way for the second one. I think we're gonna have to practice some of the trig functions as we go through. I just realized some of you guys might not know how to solve this one because you might not have taken pre-calc. And I don't think IM3 covers. Actually, IM3 honors might cover how to solve that. I think it was 0, but might not have had much practice with it because it would have been towards the end of the school year, and then this last school year, the end of it was kind of messed up. All right. Yeah. We'll see. We'll see. We shall see. All right. While you guys are working on that, let's see a couple answers here. I have an answer for number 1 already from a couple of you. Mm-hmm. Good, good. Stop this before the alarm goes off because I think it was super loud. Looks like some of you guys are still typing, so I'm gonna give you guys another minute just to finish up. It's okay if you can't get the second one, at least give me the first one. I want to know at least that you can do that one because that's similar to the ones that we did earlier, right? So see if you can figure that out. And then see how many of you guys want to try for the second one. You guys are free to go between pages now on the Pear Decks, I believe, so you can switch between the two. So you can go to the third page. That's where the h of x function is. Oh, some of you guys put number 2 into some of you guys put your h of x answers into the g of x one. That works too. I can see both answers that way as well if you want to do it that way. I made the slides so that they're on 2 separate ones. But if you put them both into one, that's fine. You don't have to do it to the second one. I can see it through here as well. But yeah, it's still working, still working. I'll give you another minute. I don't want to rush through it. I want you to try. I want you to attempt it. All right. It looks like I got 2 people who attempted the second one. 3 people. A good amount of people attempted the first one, which is good. Good. Yeah. Good amount of you attempted, at least wrote, still typing it. Not bad, not bad. Ooh, excuse me. The h of x function, though, that's a little tricky. All right. Okay, let's go ahead, take a look at this one now. Let's come back over here. Let's look at g of x real quick here. For the g of x function, right? For the g of x function, we have here x squared minus 4x plus 3 over x squared minus 3x plus 2, right? And we're focusing on these vertical asymptotes. I just realized that is over there. Vertical asymptotes, right? So we're looking for when does the denominator equal to 0, right? When does the denominator equal to 0? And it's not at x equals 0, right? And then when we figure that out, that's when we get our vertical asymptotes. So I don't want to go ahead and set the denominator equal to 0, because if I do that, I'm actually missing out on a possibility that one of those zeros might not be a vertical asymptote. It just might not, the function just might not exist at that point. So if I set this whole thing equal to 0, x squared minus 3x plus 2, set that equal to 0, and I solve this by factoring, I get x minus 3, x minus 1, x minus 2 times x minus 1, right? It looks like I get 2 undefined values at x equals to 1 and x equals to 2, right? That is where my function is undefined. It is undefined at x equals 1 and x equals 2, but I cannot make the claim that both of those are vertical asymptotes. I can only make the claim that they're undefined at that point, right? The other thing I need to do is double check if something can remove that vertical asymptote value, right? So for example, let's say here I factor out the top, I'm going to get x minus 3 times x minus 1, and in the bottom I have here x minus 2 times x minus 1. And I'm hoping you see what's going to happen with the 1 here, the x minus 1s. The x minus 1 in the top will factor out and cancel with the x minus 1 in the bottom, right? So that x minus 1, right, that x minus 1 is not a vertical asymptote. It's just an undefined point on this function. The 2 is a vertical asymptote, and that's what I would say my answer would be. The vertical asymptote is only at x equals 2, whereas x equals 1 is still undefined, but is not a vertical asymptote. X equals 1 is not a vertical asymptote. We took that point. We were able to cancel this out. And if you were to graph that, you'll actually see it at x equals 1. You're going to have that thing happen again. It's just going to look like it's approaching something, but then you're going to have a hole at that point because that function is undefined there. And that's all it is. It's not going off towards infinity. It's not going off towards negative infinity. So it's not a vertical asymptote, right? And that's it for that one. Hopefully you just got 2, right? You just got 2. Going on to this one over here now. So same thing here, but this one's a little bit different because now we're dealing with trig functions, right? The vertical asymptote, right? X equals to something. And we're basically looking at when the denominator is equal to 0. And I can't factor this. You can't factor 1 minus cosine x. I can't factor 5. So I'm just going to go ahead and look at the bottom part there and say 1 minus cosine x, when does that equal to 0, right? You got 2 ways of doing this. Easiest way is just to add the cosine over. I said 2 ways. I think there's only one way to do this. We're going to add the cosine of x over to the other side. So I have here 1 is equal to cosine of x. And when does cosine of x equal to 1? This goes to your trig practice here, right? When does the trig function cosine of x equal to positive 1? And if you remember back to your unit circle, right? Cosine's your x value. When does it equal to positive 1? And it equals at this point over here. And if you remember this, it's going to be 0, pi over 2, pi, 3 pi over 2, and of course, 2 pi, right? So when does cosine of x equal to 1? It's going to equal to 1 at x equals to 0, at x equals to 2 pi. So where do I have my vertical asymptotes? I'm going to have my vertical asymptote at 0, at 2 pi. I'm also going to have it at 4 pi. And I'm also going to have it at 6 pi. Do you know why? Because this thing rotates around, right? Here's 2 pi. Here's 4 pi. Here's 6 pi. All those values are going to have a cosine equaling to 1. And it also goes in the other direction, too. It goes in, if you learned about negative radians or negative degrees, right? It also goes this way. So not only at 0, but it also happens at negative 2 pi, negative 4 pi, negative 6 pi. So the vertical asymptotes here goes in both the positive and negative direction of these multiples of 2 pi, right? So how would I write this? So you got a couple ways. You can say, oh, it happens infinitely in the negative side, and it goes to negative 6 pi, then to negative 4 pi, then to negative 2 pi, then to 0, then to 2 pi, then to 4 pi, then to 6 pi, and then off towards infinity following that same pattern, right? If you are unfamiliar with this next way of I'm going to write it. That's one way of writing it. The traditional way, though, right, the correct way, I should say, correct way, is supposedly like this. It would be x is equal to 2k pi, right? And don't let this, if this is weird to you, don't let this throw you off, okay? Just understand that this is 2k pi. It's just a way of notation to show this without having to write all of that, right? Where x is equal to 2k pi, where k is equal to how do I put this? Where k is just an integer, right? -1, 0. There's a way to note this, and I forgot it, and I'll have to get back to you guys on this. There's a way to note the k as an integer. K is an element. This is unimportant. Okay, this is unimportant. What is an integer? It's not z, is it? Is it z? I think it's z. It doesn't matter. Well, I'll look this up later. It does. That's not the point of it. Just the point of this is the vertical asymptote for this one is going to be repeated, and it's going to be repeated every 2 pi. So when you graph this thing, right? We should take a look at this graph. Let's take a look at this real quick. Let's clear everything out. So I was looking at, let's say, 5 divided by 1 minus cosine of x. And here's the graph of it. It just looks like a bunch of u's, right? But if you look at it, at these points where the u's are not touching each other, they're getting closer and closer to each other. You see that? So that's going to be equal to, right? If I had here x equals to 0, for example, you can see I have one vertical asymptote right here at 0, because as I get closer and closer to 0, this line gets closer and closer to infinity, right? It never actually approaches a specific y value. It goes off towards infinity. Now you'll see that this does this at multiple places. It's not just 2, it's not just 2 pi, it's not just 0, it's not just negative 2 pi. It goes off infinitely, right? So technically what I could do is write it how I had it in there, which is x equals to 2k pi, right? Where k, do you not have a slider for k? Really? Interesting. There's a way that you do this. You're not going to let me add a slider? J? Add a slider for j. Well, x equals j. There we go. Add a slider for k. We'll get rid of the j. Put a 2 in front here. Hey. I gotta work on my Desmos skills here. I'm forgetting how to do this, but it's not actually that important. But you can see that when I have it like here, you can have it at 0, right? As long as k is an integer, right? So at k equals 0, we have a asymptote there. If k is equal to 1, right? If k is equal to 2, k is equal to 3, you can see that it's going to keep doing that for every single integer value for k. I'm just forgetting how to make that happen in this case. But yeah, that's that. Let's see here. Anyways, that's it for 1.2, guys. Finding your vertical asymptotes, right, is as simple as figuring out when does the denominator equal to 0, and then approaching that point to see if it goes off towards infinity or if it goes off towards negative infinity. Just because the denominator is equal to 0, though, at a specific point, doesn't make it a vertical asymptote, right? If you can remove it, if you can cancel it out, that's not a vertical asymptote. It actually just approaches some number, right? So in this particular case, at x equals 1, if I was looking at this graph, it's approaching a point. It's not approaching infinity. It's not approaching negative infinity. All right. With that, by the way, you should be able to finish up 1.2 homework now. You should be able to see where's the vertical asymptotes for those guys, and where are the horizontal asymptotes for functions. All right. Okay. We're going to move on. We're going to move on to 1.3. I'll give you guys a second to title this one, right? For 1.3, the title of this is going to be continuity at a point. Continuity at a point. So give you guys a second there. Open up a new section notes. We're going to title this 1.3, and we're looking at continuity at a point. All right. So you guys have heard of a function being continuous, right? I'm hoping. Traditionally, the most watered down way of explaining it is that you can draw a function that's continuous by drawing it without lifting your pencil. So if I can draw it all the way through, I'd say that function is continuous, right? So if I had something, for example, like let's say g of x here looked like this, and I drew it like that, would this function be continuous, or would this function be considered continuous? Right? And a lot of us would just say, yeah, you're able to draw that without lifting your pencil all the way through from beginning to end. All right? Well, then that comes down to this then. Well, okay, how about this function then? Is this function continuous? Let's say this is f of x. All right? Let's say f of x here, again. This, by the way, is the function 1 over x, right? Would you say that 1 over x is a continuous function? Probably not, right? You can see that it's not continuous because, well, I had to lift my pencil up to draw it from here and then draw it to here, right? And then how about this then? What if I had the function the square root of x? And I graph that, and it's this point like this, and it looks like that. Would you say that function is continuous? You don't know. Or maybe you do. Or maybe you're just wondering what the heck is knocking me going on about. Yes. And since he's going with yes, he's just going to jump into it. Yeah. Yeah, it looks continuous, right? I drew it without lifting my pencil as I drew it along the way. All right. How about this? What about a function that looks like this? You ready? Is that function continuous? Yes or no? What do you think? This function right here, this random function, let's call it h of x. Would you say this function is continuous? Yeah? I lifted my pencil up though, right? To draw this little hole right here. So this function is going here. And then I had to pick up my pencil, draw a hole, and then draw this over here, and then I draw a solid dot, and then I drew it up. Like I was going, no, no. Some people, yeah. Now this is hard to do actually. If you think about this, and you're like, nah, this is hard. You just say yes or no. It's yes, no. Yeah, Max, exactly. Like you're saying yes, no, right? But we're not actually proving that it's a continuous function, are we? Right, and that's because to prove if a function is continuous is actually really hard. You have to show for all the points of that function going through. Right, so we don't necessarily do that too much. We mostly focus on continuity just at a specific point. Right, it makes it a little bit easier. We look to see, is a function continuous over an interval or at a specific point? We don't actually look at it for all the possible points. That's just really hard to do because I don't know what it's going to do towards infinity or negative infinity for every single function. Right? Some functions might do the same consistent trends, but some of them might do something crazy. It might be piecewise. It might be something like that. So what we talk about then when we're talking about the definition of continuous, right, is usually these rules right here. Give me a second there. Let's drill that down. So if I'm looking at if a function is continuous, right, I'm going to add on to this definition of continuous at a point. Right? A function is continuous at a point if it meets three conditions. Three conditions. Those three conditions are: condition number one, a function is continuous at a point if yeah, here we go. First condition. The limit as x approaches that point a from the positive side of f of x and the limit as x approaches a from the negative side of f of x exists. If the limit from the left-hand side and the limit from the right-hand side of the function exists, the first condition is met. And what does it mean for it to exist? It basically means that from the left-hand side, it approaches a point, and from the right-hand side, it also approaches a point. Okay? That's the first condition. It needs to exist. The second condition is that the limit as x approaches a from the positive side of f of x is equal to the limit as x approaches a from the negative side of f of x. So if I were looking at a function that we agreed was continuous, this guy right here, and I had some random point a, right? What I've essentially shown, right, or what I'm essentially talking about is if I was to approach that function from the right-hand side, it'd be coming in like this, and it'd be approaching this point right here. And I approached it from the left-hand side, from the negative side, it's approaching it like this, and it's approaching it right there. Both those limits exist. The limit from the left-hand side and the limit from the right-hand side exists. That's the first condition, and the first condition is met. Second condition is that the limit from the left-hand side and the limit from the right-hand side both approach the same number, meaning they both equal to each other. So the left-hand limit, this blue one, is equal to the right-hand limit, this red one, right? They both approach the same point. And if that's the case, that's the second condition met. The last condition is the function itself evaluated at a. The function itself evaluated at a needs to equal to the limit as x approaches a of the function, of the said function. Now you say, well, yeah, the function right here exists at that point that it's approaching, so the function is equal to what the limit is of that function from both sides. So yeah, that is continuous by definition that we have here, right? It follows those three situations. It needs to not only have the limit from the left-hand side equal to the limit from the right-hand side, they have to approach the same value, and the function value has to exist at that same limit, right? So you'll have problems where it looks like it's continuous, right? But it doesn't meet all three conditions. And if that's the case, then I wouldn't say that it's continuous at that point, right? So for example, let's say I have here, a function that looks something like this, right? If I had a function that looked like this, it meets, and this is my a right here, right? It meets two of the conditions, right? I'll show you right now. What's the third condition? The third condition is saying that the function is equal to the limit value at that function. So let's take a look here. So check this out. Here's one where it doesn't meet that third condition, right? So let's say here, it is approaching from the negative side. So it's approaching this value right here, right? So the limit of f of x is approaching this point from the left side, and it's approaching the same point from the right side. So I would say that the first two conditions are met. The limit exists from the left-hand side and the right-hand side, and they equal each other. But the function, let's say then, is equal to some random point up here. Then the third condition fails on this one. I'd say that this function, right, is not continuous at a, because the function f of a is up here and the limit is down here. So f of a does not equal to what the limit function value is, right? And that's all it is to define something as continuous, that it needs to have a limit that exists, right? And the function value has to equal to that limit value, okay? You're probably wondering, like, what? Because that's what I thought too when I went through this. It's basically a set of rules that you need to have there to show that it's continuous at a point. And those rules are as follows. As always, does the limit exist as it approaches from the left side and the right side? Do those limits equal each other? And does the function equal to that limit at that point? If it doesn't, if it fails on any of these ones, you would say that the limit, you would say that that function is not continuous at that point. And that's the key factor there. If it fails to meet one of these three criteria, you would say that the limit is not continuous at that point. All right? So let's take a look at a problem. Let's take a look at a problem here. I have two examples here. Let me scroll this one down so we have a little bit more space. Get out of the way. Get out of the way. Okay, so let's verify that f of x is equal to x squared is continuous at x equals 2, right? Let's verify that this thing is continuous at x equals 2. I know some of you guys are like, knock me, I already know this thing is continuous. It's a parabola, right? But let's go with the definition of continuity, right? Let's go with the definition of it. So I have this function here, f of x is equal to x squared. So to verify that this is continuous, I need to make sure that the limit from the right-hand side is equal to the limit from the it exists, and that it equals to the limit to the left-hand side. So first condition, right? First condition, check to see if those limits exist. So I'm going to check if the limit as x approaches 2 from the positive side of f of x, check if that thing exists first of all. And since we're dealing with x squared, I should have just wrote that as x squared, right? Well, that's just going to be, what's the limit as x approaches 2 from the positive side of x squared? That's just going to be equal to 4, right? And then this, still on the first condition, I need to check that the limit as x approaches 2 from the negative side of x squared, I need to check that that also exists. And it does, right? 2 from the negative side is also going to be equal to 4. So that right there is the first condition. The limit from the left side and the limit from the right side exist. Second condition, do those limits equal each other? Yes, it does, right? 4 is equal to 4, so the limit from the left side is equal to the limit from the right side. So the second condition is met. So I've met 2 out of the 3 conditions. I've met that, hey, the limit from the right side exists, and so does the limit from the left side. And the limit from the right side is equal to the limit to the left side. So those 2 conditions are met. Now the last one is the third condition. Does the function exist at that point where the limit is equal to, right? So what is f of 2 in this case? F of 2 is just plugging it into that function. So you have here 2 squared, and that's equal to 4 as well. And you can see that does equal to the limit from the left side and the right side. So I can say that f of 2 is equal to the limit as x approaches 2 of x squared. Does that make sense? So I've checked that off now. Now it verifies it at the third point as well. So I can say yes, f of x is continuous at x equals 2 because of those 3 conditions, right? I've checked off the first condition, I check off. So the first condition is that they exist. The second condition is that they equal to each other. And the third condition is that the function is equal to that said limit, right? So it checks off there as well. And I can say, yes, this thing is continuous. And this is a boring example because it's x squared. We already know x squared is continuous because, you know, it's a function that we're both familiar with, or we're all familiar with. So let's go into a more unique one then. When do they, well, when are they not as straightforward? And that's going to be the case when you deal with piecewise functions, right? Are you familiar with these piecewise functions? A piecewise function like this is something that's broken up at a specific x value, right? It could be broken up at x equals, in this case, 3. So when x is less than 3, my function is going to be following this guy. Whereas when x is greater than or equal to 3, it'll be following this one instead, right? So I want to check, right? I don't have any rules written down for this one. Right? We're going to verify, right, that f of x is continuous at, in this case, x equals 3. We're going to verify that this thing is continuous at x equals 3. Right? So again, we go through those conditions, right? We look to see, hey, what's the limit as x approaches 3 from the negative side of this said function, right? And I'm hoping you guys see this. When I'm approaching 3 from the negative side, I'm looking at it from the first part because x is less than 3, right? That's what it means to approach from the negative side. I'm approaching it from the numbers that are less than 3 side, right? The left side. So as I'm coming from that side, right, what does that equal to? And I'm hoping you guys will see that if I were to look at this, then this is going to be equal to 2 times 3 plus 3, which is going to be equal to 9, right? The limit exists, by the way. The function doesn't exist at 3 for this part right here, but it approaches 9, right? And then we do the same thing, and we look at the limit as x approaches 3 from the positive side of f of x, which would be equal to 3 squared, which is also equal to 9. So the first condition is met. The limit exists from both the left side and the right side, right? First condition checks out. Second condition, does the left-hand limit equal to the right-hand limit? And it does. Second condition is met. Now the last but not least is the third condition, and that's asking, well, what the heck is the function equal to at 3, right? Well, if it's equal to 3, I need to be focused on this one because that's when x is greater than or equal to 3. So that means I need to focus on this function down here and say, oh, that's just equal to 3 squared, which is also equal to 9, which also equals to what the limit equals to. So the third condition is met. So I would say, yes, this function is continuous at x equals 3. Now, this whole thing of going through all this is basically just understanding that you're going through 3 check marks. You're checking to see, does the limit exist from the left side or the right side? Do the limits equal to each other on the left side and the right side? And does the function equal to that limit? If all 3 conditions are met, you can say that that function is continuous at that point, right? And you can do this for infinitely many points. I could do this at x equals 2, x equals 1, x equals whatever. But you mainly focus on where there might be a disconnect between the two. How are 1 and 2 different? They're not, Ren. I would actually say that condition 2 can only exist if condition 1 works, but that's how they define it in the calculus world. I know it seems like it's a little redundant, right? But they make that statement for condition 1 to be able to make the statement for condition 2. But I always thought that was weird, but you can't say that without saying that for condition 1. But I was proven wrong, by the way. You can say that they can equal to each other if they both go off towards infinity, and that leads into a whole nother rabbit hole of the discussion. So let me show you an example. This isn't for your notes, guys. This is just for interest sake. Let's say I had here this point right here, right? And I was looking at the limit as it approaches from the left-hand side, and it goes like that. And then I looked at the limit as it approaches from the right-hand side, and it goes like that, right? You would agree then that in blue, I would say that the limit as x approaches a from the negative side, we'll just say that this is a right here, right, of this function, f of x is equal to infinity. And then you can say the limit over here as x approaches a from the positive side of f of x is also equal to infinity, right? So that's why in condition 2, some people would make that claim that said, oh, this limit is equal to the left and is equal to the right. But it doesn't meet the first condition, which is that limit doesn't actually exist, right? Infinity is not a number, right? They're both equal to infinity, which technically they're equal to each other. But then this goes to an whole other conversation, right? But if you want to just focus on that, that's the reason why they have it as a 1 and 2 separate, Brandon. It's just for that sake. It's just like, well, the limit doesn't actually exist in this case. And also, if they were to accept it, then you can clearly see this is not a continuous function at a, right? It's not continuous at all. So that's why they make it to that they have that first step and the second one separated from each other, just simply for that sake. But I agree with you, Brandon. I would say that's kind of pointless, because when you work these problems out yourself, you're gonna see that, like, oh, if they equal to each other, it already matches the first and the second condition. But teach their own. Anyways, that's how we check to see if something is continuous. When something is not continuous, we have this thing called a discontinuity, right? Discontinuity is basically a fancy way of saying, like, there's a disconnect there, right? It's no longer continuous. There's some way that's breaking the continuity. And there are 3 different types of discontinuities. The first one up is a removable discontinuity. Let me show you a removable discontinuity, right? For a removable discontinuity, it looks something like this. You'll have a graph, and it'll be coming along like so, and then you'll have a hole. That hole is your removable discontinuity, right? The function there doesn't exist at that point, so it fails the third condition. And since it fails the third condition, we say that it's discontinuous at that point, wherever that point is. And usually it looks something along the lines of this. I could have something where it's like x minus 2 times x minus 1 over x minus 2, right? Since I'm able to factor and cancel these points right there, that creates a hole. And that hole is your removable discontinuity, okay? So if you're working through, you have this is one of the 3 types of discontinuities, right? Removable discontinuity. A second one is going to be this thing called a jump discontinuity. Jump discontinuities are interesting in a sense that they look like this. So I have something where it's working along and it goes to here and it has an open dot, and then it is defined up here and then continues like so, right? That's a jump discontinuity. And jump discontinuities, right, usually come in the sense of like these weird functions. One weird function is something that looks like this, which is the rounding function, I guess is what it's called, right? It's the rounding function. They also have ones that are called step. Hold on a second. They also have ones that are called like the floor function or the ceiling function. If any of you guys are in coding, right? The floor function will round everything down every single time. The ceiling function will round everything up. Those functions are actual functions, by the way, and these are clearly discontinuities because the left side limit and the right side limit don't equal to each other, right? So that's it already fails at the second step. But for those who aren't familiar with this one, this function would take basically, if you had a decimal like 2.3, and it'll just round it for you. There's that one, and then if you could plug in 2.5, it'll round it to 3 for you. And those guys are actually neat. If you guys go and look into Desmos, they actually have that function in here. Give me a second. Let me find it. Function miscellaneous, and it is the rounding function. So if I had the rounding function like that, check it out. If you were to look at these guys, so when x is equal to 1, it just equals to 1. But if it goes to and equals to 1.2 or 1.3 or 1.4, it gets rounded down to 1, right? But then at 1.5, it's equal to 2. See that? So right here, it actually gets really, really close to 1.5, but it'll never touch it. So you'll have like an open hole here, whereas up here, you'll have a solid hole at 1.5. Because at 1.5, you then round it to 2, right? So that's a jump discontinuity. You can see, and it makes sense, right? Why it's called a jump discontinuity, because it runs up to here and then it jumps to the next one, right? It runs up to here and then it jumps to the next one as well. So that's that. Let's see here. That's the jump discontinuity. And the third one is the infinite discontinuity. Infinite discontinuity. Infinite discontinuity is when your function goes off towards infinity. So if I have something like this. So I have a function that's on the left-hand side and it's going off towards infinity. And I have a function that's coming from the right-hand side and it also goes off towards infinity. And you can also have it go towards negative infinity as well, right? It doesn't matter if it goes off towards positive or negative infinity. It's just going off forever, right? And those functions tend to look something along the lines of like, you know, the stuff that we've been looking at. So f of x is equal to 1 over x squared, for example, is one of them that has a infinite discontinuity at x equals 0. But you also have the ones where you factor and nothing cancels. So you can have something like this. X plus 1 is equal to x squared, x plus 2 times x plus 3, right? When your factors don't cancel, at -2 and -3, for example, here in this case, I'd have a infinite discontinuity at x equals -2 and x equals -3. Okay, so just keep that in mind. You are going to have to know these three discontinuities just because when you're dealing with limits, if you can tell that it's a certain type of discontinuity, you can figure out if the limit is going to exist there or not, or if the function is, when we talk about it, like differentiable, right, when we get to that. But basically, one that limits can really work with are the removable discontinuities, because with the removable one, you can say that the limit exists as it approaches from left to right. Whereas the jump discontinuity, they exist, but they don't approach the same number. And for infinite discontinuities, they straight out just go towards infinity, and the limits just straight up don't exist at those points. All right, I'm running out of time. Right? This is where we're going to continue from next time. If you guys want to copy this down, is finding a value for a removable discontinuity and making something continuous. And basically we're going to be looking at a graph and saying, oh, what can I make this specific value for k so that the two functions line up and I can say that they're continuous, right? But we only have 4 minutes. I'm going to show you a graph of it instead. I'm going to show you a graph of this one right here, and we'll call it a day there. So let me go ahead and show you this graph real quick because I think it's neat. So if you guys take a look here real quick. So here's a graph, right? I have it broken up into two pieces, one red and one blue, right? So it's broken up at 3, at x equals 3 here, right? So if I have x is less than 3, it follows this parabola. If I have x is greater than 3, it follows this line where k is equal to 2 right now, okay? So when k is equal to 2, I hope you guys can see the limit as it approaches from the left side is equal to the limit as it approaches from the right side, and the function exists at that point that they both approach, right? They both approach 6. You see how it's approaching 6 right here? It's 5.9, 5.96, 5.97, right? And this one goes down to 6.1, 6.08, 6.06. So they're both approaching the same number, and the function exists right there as well. So this is continuous, yeah? And a continuous function. Now, if I change the k value, boop, you guys can see, right? Just by moving this piece up a little bit, it's no longer continuous. It's approaching this on the left-hand side, so the limit still exists, and approaches from the right-hand side, so that limit exists as well from the left and the right. But now the two limits don't equal each other, right? Now the two limits don't equal each other, so it fails condition 2. So what we're going to do next time is we're going to be given a problem, and we're going to have to find out what k needs to equal to so that we can meet those 3 conditions, that the left-hand limit equals to the right-hand limit, and the function equals to that said limit as well. So you guys see here, this is kind of neat. I hope you guys can see that at least, right? As I keep moving this along, you can clearly see when the function is discontinuous and when is the function continuous. This one I made up as a simple one because it equals 2 at 2, but we're going to do problems where we're going to have to find out, how do we find out that k value so that is equal to it without having like this tool that moves it around for us. Isn't that kind of neat though, right? Look at this. Check this out. Right there. All right, so we're in the middle of 1.3 right now. I'll put the homework up later, but I don't know if you'll be able to do them. At least, I don't even think you'll be able to do the first ones, but I'll put that up. But you guys should be able to finish 1.2 now. You can get in there. I know that I heard that the Google Drive was down today for right now, so Cami might not be working correctly. But if it isn't, just wait for it sometime. I know I set the due date to this Friday, but it's not a hard deadline, right? It's a hard deadline for when we actually take the test. So don't worry about that for now. Just get in there and finish 1.2 when you can. All right, and that's it for me, guys. I'll see you guys later. Hopefully it wasn't too much or too crazy. And yeah, we'll continue this on Thursday, all right? And that's it for me, guys. I'll see you guys later, all right? Have a good one.